This lesson is about learning how to find multiplicative inverses of matrices and then using those inverses to solve systems of equations. First, let's talk about the identity matrix. We discussed the identity matrix and its properties in the previous lesson. We know that AI equals A and that IA equals A, meaning that we need to multiply the identity times a matrix and get back it's the same matrix. That's because it's the identity. But we need to perform the multiplication on both sides because matrices are not commutative, as we learned in the previous lesson as well. So, as shown, we need to multiply AI to get A and IA to get A. A little notation, side note, on the identity matrix. We call it matrix I, and then we denote the size. So, as this matrix is a 2 by 2, we would call it I2. If the identity matrix was a 3 by 3, we would call it I3, so on and so forth. Now, the multiplicative inverse of a matrix. The inverse needs to work on both sides, just like the identity matrix. So, if we're given a matrix A that is n by n in size, note that it is n by n, meaning that it must be a square matrix. Therefore, we cannot find the inverse of a non-square matrix. So, if A is n by n, if there exists an n by n matrix A inverse, meaning there may not always be an inverse. So, if there exists an inverse, then A inverse equals IN and A inverse A equals IN. If both are true, then A inverse is the multiplicative inverse of A. Sometimes it doesn't work out that both sides give us IN. If only one side gives us IN, then that matrix would not be a full inverse. If it's only a one-sided inverse, we would call it a one-sided inverse or a right inverse or a left inverse. That does sometimes happen. It is not common, but it does happen sometimes. Generally, though, a matrix either does or does not have a full inverse. So, as shown in this example, we have A times B giving us I2 and B times A giving us I2. Therefore, B is the multiplicative inverse of A, or B equals A inverse. Now, if a square matrix has a multiplicative inverse, then that matrix is said to be invertible, or sometimes we call it non-singular. And that inverse is unique. Just like 5 only has the inverse of 1/5, A only has the inverse of B in the previous example. If a matrix does not have a multiplicative inverse, that means we call that matrix singular or non-invertible. Now, let's look at an example. If we're given the matrix A and A inverse, we need to prove that it is actually A inverse by proving that A inverse equals I2 and that A inverse A equals I2. So, let's perform the multiplication. So, when we see performing the normal multiplication rules with matrices, when we multiply A times A inverse, we get the matrix I2. We also see that when we multiply A inverse times A, we also get I2. Therefore, A inverse is truly the inverse of matrix A. So now let's find how to actually find the inverse matrix. Now, there are a couple different ways to do this for a 2 by 2 only. We are given a quick method for finding a matrix for a 2 by 2, but the longer method that we'll learn afterwards that works for larger matrices also works for 2 by 2s. So, if we're given a matrix A that it has entries A, B, C, and D, to find A inverse, first we need to find the scalar quantity of 1 over the AD minus BC. Notice that AD minus BC, it's almost like we're cross multiplying, like we do with proportions. Okay, so first we find that scalar. Then we do a little transformation on the original A matrix. That transformation is on the first top right left to bottom right diagonal. We switch the quantities A and D. We don't change them at all, we just switch them. Next, what we do is with the second diagonal from bottom left to top right, is we don't switch them this time, we multiply them by -1. We change their signs. So all we do is switch A and D and change the signs of B and C. So let's do an example with the matrix A of -1, -2, 3, and 4. So first find the scalar of 1 over AD minus BC. We see that that is 1 over -1 times 4 minus -2 times 3. Simplifies down to just being 1/2. Then let's transform the matrix. We switch A and D, meaning all we do is switch -1 and 4 to their opposite positions. Then we leave 3 and -2 where they are, but change their signs. So -2 becomes +2, and 3 becomes -3. Next, all we do is multiply the scalar of 1/2 through the matrix to end up with the simplified matrix of 2, 1, -3/2, and -1/2. That matrix is A inverse. If we were to perform the multiplication of A times A inverse and A inverse times A, we would get I2 from it. Okay, so let's perform another example. If we're given the matrix -3, 2, 1, -4, let's find its inverse using that quick method that we discussed in the previous slide. Now, first find the scalar. It is also a good thing to identify each quantity as A, B, C, and D so that throughout the process you know exactly what A, B, C, and D started out as so that you know that you're performing the correct method. So first we find the scalar to be 1 over -3 times -4 minus 1 times 2. That simplifies down to be 1/10. Then the transformed matrix changes to be -4, -2, -1, and -3 by switching A and D and changing the sign of B and C. Okay, then all we do is multiply that scalar of 1/10 through the transformed matrix to get -2/5, -1/5, -1/10, and -3/10. That matrix is A inverse. Okay, let's look at another example. This matrix that we're given does not have a multiplicative inverse. So remember, the only way that can happen is if that scalar has something wrong with it. The only thing that can happen is if the denominator of AD minus BC equals 0. So first identify A, B, C, and D, we see that we get 1 over -3 times -4 minus 2 times 6. And we know that that gives us 1 over 0. That is undefined for us. So we know that A is a singular or non-invertible matrix. Okay, now let's move on and have you try this question on your own. Now pause the video and try it yourself. Okay, now let's go through this question a little bit again together. First, I hope everyone identified A, B, C, and D, then found the scalar of 1 over AD minus BC, then transformed the matrix of switching A and D and changing the signs of B and C. Then all you have to do is multiply the scalar, the simplified scalar of -1/13 times the transformed matrix, and then simplify to get -5/13, 3/13, 1/13, and 2/13. Okay, now let's move on to how to find the multiplicative inverse of a larger matrix. Now we know that quick method. Sometimes we don't always remember those little quick simple ways of not doing the longer method. If you were to forget how to transform the matrix per se, you can always perform this longer method that works for larger matrices. Now that quick method, remember, only works for 2x2s, does not work for a larger matrix. So the procedure for finding a larger matrix multiplicative inverse. So if the matrix is invertible, now we cannot look at a matrix and know if it's invertible or not, but if it's invertible, we would find through this process that it works. If it is not invertible, the problem would happen in step 2 of performing row operations. We would get something like the matrix of 1 0 0 0 1 0 0 0 0, such as that matrix would want to be transforming into the identity matrix but cannot. If that happens, then the original A matrix is singular or non-invertible. Okay, now let's go through these procedures step by step. The first step would be to form the augmented matrix of A, the given matrix, joined with the identity matrix of the same size. Now remember, A must be a square matrix. So, when we form the augmented matrix, we then want to perform row operations on the entire augmented matrix to transform the matrices into IN conjoined with a matrix B. Okay, so when we perform those row operations and get matrix B, that matrix is A inverse. Now you can always verify your result by performing the steps of multiplying A times A inverse and A inverse A to get IN. Now let's summarize the previous procedures. If the matrix that you're given to find an inverse of is a 2x2, you can use the quick method. If it is larger, you can use the previous procedures. Now, remember, you can use the not quick method for a 2 by 2 if you forget the exact way to use the quick method. Also remember, if using the quick method you get AD minus BC equals 0, then the 2 by 2 matrix does not have a multiplicative inverse. Okay, now let's go through an example of finding the multiplicative inverse of a 3 by 3 matrix. If we're given this A matrix, first we would find the augmented matrix of A joined with I3, then perform row operations. Now let's remember what row operations are. The first type of row operation is adding and subtracting different rows from each other to replace a specific row. Now, we can just add and subtract, or shown, we can subtract a multiple of a row from another row. As shown in the third step, we want to take row 3 minus 3 of row 2. Okay, then the second row operation is multiplying a row by a scalar. In the fourth step shown, we're multiplying row 3 by 1/4. So because in row 3 we have 0, 4, 0, and we're trying to get to the identity matrix, we want to make that 4 into a 1, so we multiply by 1/4. Then the third row operation is switching rows, as shown in the sixth step of switching row 2 and row 3. Now let's go through the different steps shown, and we see through all 6 steps of row operations, we finally get the final augmented matrix of I3 joined with B. And then we know that B is really A inverse. And we can check that by multiplying A and A inverse and A inverse with A to get I3. If you ever multiply and do not get I3, then generally that means that you performed a row operation somewhere incorrectly. So go back through and check your steps. If you have trouble with row operations, such as the previously shown third step of taking row 3 minus 3 of row 2, instead of trying to do it all at once, maybe on the side, write out what 3 of row 2 is. Then subtract those numbers from row 3 and replace row 3. Also, don't try to do 2 steps at once. As you get better with matrices and row operations specifically, you can more quickly find the row operations and do multiples at the same time. But when we're just starting out like this, it's much better to take your time and do one at a time instead of trying to hurry through it and make those mistakes. Okay, now let's move on and try a question on our own. So, pause the video and try it yourself. Now that you've gone through it yourself, let's go through the steps together. Now remember, because with math, there's always multiple ways to perform any question. If you did not perform the exact same row operations, but you got the same A inverse matrix, that's fine, okay? So, if you had any trouble finding A inverse, pause the video again and go through my steps and see maybe where you made a mistake, okay, or where you had trouble. If you have trouble starting, okay, just try to eliminate numbers, okay? So notice in my first step, I took row 1 and eliminated the 2 in row 3 in the first column, even though the row 3 had a 0 in the third column, and I then got rid of the 0 and kind of added a number there where I didn't have one before. That's okay. Because we got rid of the number in the first column, we are well on our way to getting to the identity matrix. Okay? Then after that, what I did was I wanted to then get rid of that number that I just added in. Okay? So you can see that I got rid of the 4 that happened because of the -2 in row 1. And then that third row only has a single number. And then we can use that to get rid of numbers in that column in rows 1 and 2. Okay, now let's move on to how we can use those multiplicative inverses in systems of equations. Okay, so if we're given a systems of equation, such as the linear system shown, we can write that linear system as an equation of matrices. Okay, we would form the matrix equation of the first matrix of the coefficients, just like a normal matrix. Okay, then another matrix with all of the variables. Okay, we would call that matrix capital X. Then we would set it equal to the solution matrix, or the solutions of the linear system. Okay, so notice because the second equation in the linear system does not have any x's, we then write a 0 in that column of row 2. Okay, then because the third equation does not have any z's, we would write a 0 in column 3 of row 3. Okay, so we're given that linear equation with matrices of A times capital X equals B. Okay, then if per se the linear system had a fourth variable, we know that we would need a fourth equation. So A would then be a 4x4 matrix, and the X matrix, the variable matrix, would instead of being a 3x1 would be a 4x1 matrix. And then the solution matrix would be a 4x1 matrix as well. Okay, so how do we use the inverse in this linear system? We take the matrix equation of AX equals B, and then we want to get rid of A. We want to solve for X, okay? So the normal way of solving for X would be to undo what's happening. So if multiplication is happening, we would normally divide, but we know that we cannot divide by matrices. So instead of dividing, we would multiply by the inverse of A. So, and we know that order matters with matrices because they are not commutative. So that means since A is on the left side of X, we must multiply by A inverse on the left side of A. Okay? Because we multiply by A inverse on the left of A, we must also multiply by A inverse on the left of B, as shown in pink. Now we know that A inverse times A gives us IN, and then we know that IN times any matrix of size n by anything, in this case n by 1, we know that that gives us just that matrix. So IN times X just gives us X. Then A inverse times B is the solution set, okay? So let's look at an example. If we're given this linear system, first we need to write out the different matrices that involve this linear equation. We know that the linear equation first setup just has a times x equals b. But then we know that we need to use the multiplicative inverse. So go ahead when we're first starting out and also find a inverse. Okay, so we know that matrix A, because of the coefficients, is 1, 0, 1, 1, negative 1, 0, and 1, negative 1, 2. We know that because we only have x, y, and z, that the variable matrix is x, y, z, which is a 3 by 1. And then the solution matrix is 3, negative 2, 2. Okay? Then, by performing the previous procedure to find A inverse, we find A inverse to be 1, 1 half, negative 1 half, 1, negative 1 half, negative 1 half, 0, negative 1 half, and 1 half. Then we perform the previous multiplication on the former slide. Okay, now we go through this with the actual matrices to have A times x equals b, then multiplying by the inverse to have A inverse times A times x equals A inverse times b, and then that simplifies to being I3 times x equals A inverse times b, and then we perform the multiplication of A inverse times b to get the matrix 1, 3, 2, and then that tells us that x equals 1, y equals 3, and z equals 2. Now you can take those values and plug them into the given equations, and then we would see that those are the solution to that system. And then we know that that is the only solution to the system. No other numbers would work. Now, let's move on and have you try this out on your own. So remember, first write out what matrices A inverse, X, and B are. Then perform the multiplication. So pause the video and try it yourself. Now that you've tried it yourself, let's make sure that we have all the same matrices. So first, we have the coefficient matrix of A, then performing row operations with the augmented form, we find A inverse to be negative 2, negative 2, negative 3, 1, 1, 1, negative 2, negative 1, negative 2. Then we have the matrices X and B. Now going through the multiplication, we would have A times X equals B, A inverse times A times X equals A inverse times B, to have X equals negative 13, 6, negative 9. Now hopefully everyone found those. If you had a different A inverse matrix, check your row operations and see where your mistake happened. Then, hopefully then if your A inverse was correct, you went through the correct procedure to find the given solution set. Now let's summarize the lesson. First, we discussed the multiplicative identity that we first discussed in the previous lesson, and that we know that we have to multiply AI together to get A and IA to get A. Okay, so it's a two-sided identity. Next, we discussed the multiplicative inverse and how to find it. So with a 2 by 2, we have two options. First, we have the quick method. Then we also have the larger matrices method, okay? So both ways work for a 2 by 2. But if you have a larger, so anything 3 by 3 or bigger, you have to use the augmented matrices form with row operations to find the inverse, okay? And then we learned about how to use multiplicative inverses in linear systems. Okay, so I hope that you enjoyed the lesson. If you have any questions, go back through the video and hopefully you can work out any issues. If not, make sure to ask any questions that you still have.